Yeah. Okay, so one last little thing I forgot to. You guys want to do that? Stretch while the administrator walks in, you get your desk right away. So here's the thing. So I forgot to tell you one little thing about this. We talked about this stromatolites yesterday. I left myself a note. So this is interesting. So you can go back and you can look at those cross sections. And I had, where was that picture I had just? This thing, right? You look at the daily growth rings superimposed over the yearly growth rings, and you can calculate that the Earth had 450 days in a year, but a year has always been the same length, right? So yes, the Earth was rotating faster, but the Moon was a lot closer. The Moon has receded dramatically, and as a consequence of that, the exchange of energy between the Moon and the Earth has slowed the Earth's rotation down. Okay, but there's an end game to this, which ultimately won't be good. And eventually, what's going to happen to the Moon? It's going to go away. It's going to go away. It's going to keep receding, and at some point, it's going to go away to the point where it's no longer going to be in orbit. And then we won't have a moon, and that would cause some problems, actually. But you won't have to worry about it. That's in the distant future. It would do lots of things. Yeah, it would.
How long does it take?
What's that?
How long would it take to go?
I don't remember. But it's billions of years, so we're fine.
So we wouldn't rotate anymore when it was gone. Is that what you're saying?
No, that wouldn't be it. That wouldn't be it. Our days will continue to get longer, though. Yeah.
But,
What would it do?
So what it would do to the oceans is you wouldn't have tides, and tides turn out to be important because tides stimulate the movement of water into inland seas. And without that, you wouldn't have exchanges of nutrients, and it would cause lots of problems. The Earth is really pretty finely tuned. You mess with things and it's not good. Yeah, things can go out of whack in ways that are not predictable. Okay, yeah. Well, it will eventually figure something out, but if we want to live on it, that's the problem. So here's what I want to look at today then. So I want to talk to you about, I started to mention this, about how this Cavendish experiment, this was really amazing. This guy essentially found the mass of the Earth inside of a lab. And here's how he did it. So we knew that gravitational force was proportional to the products of the masses of the two objects, right? That we knew. You get two objects, if the mass is increased, then the gravitational attraction between them increases accordingly. We also knew, and Newton had shown us this, that it was an inverse square law, right? It obeyed the inverse square law. So it was inversely proportional to the square of the distances between the objects. But what we did not know is what the constant was that related those things, right? The gravitational force is so small that experimentally it's extremely difficult to measure that constant. But do you see that if we had known that, that would have allowed us to find the mass of the Earth, right? Because think about this. Think about the stuff that we know in this equation about Earth. I could use anything. I mean, we could take a kilogram of lead, for example, right? A kilogram of lead is a kilogram of lead. It has a weight of what on Earth?
1 kilogram.
No, that's its mass. What's its weight? 9.8 newtons, right? Okay, so we know, look at the stuff that we know. We'll just circle the things that we know. Well, we know the weight, the gravitational force, would be 9.8 newtons. We know its mass, and we actually even know how far it is from the center of the Earth. We've known for a long time. Let's see. No, she's not. We've known for a long time the radius of the Earth, and I started to talk to you about this yesterday. I'm going to skip forward, and I'll show this to you now. I kind of predicted the order would be different. We'd look at this stuff, but watch this quick little video. This is kind of cool.
Ooh. So is this constant? 130.
In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth. 40,030 kilometers. But over 2,000 years earlier in ancient Greece, a man arrived at nearly that exact same figure by putting a stick in there.
240 BC.
That man was Eratosthenes. a Greek mathematician and the head of the Library of Alexandria. Eratosthenes had heard that in Syene, a city to the south of Alexandria, no vertical shadows were cast at noon on the summer solstice. The sun was directly overhead. He put a stick vertically in the ground and waited to see if a shadow would be cast at noon. It turns out there was one, and it measured about 7 degrees. Now, if the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow while a stick in Syene is not, it must mean that the Earth's surface is curved. And Eratosthenes probably already knew that. The idea of a spherical Earth was floated by Pythagoras around 500 BC and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. Since the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities and learned they were 5,000 stadia apart, which is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees. So 800 kilometers times 50 equals 40,000 kilometers. And just like that, a man 2,200 years ago found the circumference of the entire planet with just a stick and his brain.
That's kind of cool, right?
Well, look at that video on the side.
Did he know what he found, or like
Yeah, he did.
he knew that was gonna come out to be the circumference?
Well, no, he didn't. He didn't know. No, that's
40,000.
he knew it was going to be. He knew this would work, but he didn't know what the answer would be. So he actually, I mean, this has been known for a long time, right? So we know what the radius. That tells us what the radius of the Earth is, and so we know what its square would be too. Just square it. So what's the only thing missing here, then, right? If we knew what G was, we were missing these two, right? We're missing the universal gravitation constant and the mass of the Earth, right? We're saying this is the mass of the lead. This would be the mass of the Earth, right? So if we knew what that was, we would know the mass of the Earth, right? We could do it in our classroom. We could calculate it right now. It'd be an easy calculation, right? So we just need to know what the mass or what the universal gravitation constant is. So here's how it was accomplished. This is really cool. So this is just kind of a schematic of the Cavendish setup that he had. He had this building, he enclosed it so there could be no air currents that disturbed anything. And what he had this real sensitive torsional balance up here where he could, by pulling on this little wire, he could twist this torsional bar that had attached to it these very large lead spheres. And they were really big, I mean hundreds of pounds. He had a second torsional rod in there, which hung down in the middle, which had two small lead spheres. And when he brought those into close proximity, he could measure how much the force of gravity caused those to get pulled together, because it would twist this wire a little bit, right? That's a pretty elegant design. I mean, he had this thing, they don't talk about this in any of this stuff online, but he calibrated this. We already knew a lot about electricity and magnetism at the time. We knew that if we put charges on these metal spheres, they would produce a known electromagnetic force of attraction. And then we could, by putting known amounts of charges on there, we could measure how much this wire twisted and calibrate the instrument that way, right? So we'd know these very small forces, a very small force produces this much twist, and this much produces this much. And you could make a scale out of it, right? You could calibrate it that way. And so here's kind of what he ended up doing then, right? When he swung this bar into place, the small spheres would get attracted to the large ones. And he had a light source. His wasn't a laser because they weren't invented at the time, but he used a bright sodium vapor beam. But now we'd use a laser. Just bounce a laser off this mirror and see how far it gets deflected, right? So here's just another, you can see here's the torsional wire, and this is the one that's getting attracted. It's getting twisted a little bit gravitationally, right? There's an actual mock-up of not the actual apparatus, but a replica. And just some other pictures I threw on here, so they'll be, I don't know if they add anything extra. This is a pretty good one right here. This is how You could do it in a modern lab pretty easily. And then I have a little video. That's how you could measure the gravitational force between those spheres. So I got one more that's a good one. Let's see, where is this? Right here. Yeah, look at this one. It's really short, but it just kind of shows you how this thing works. So you put the large spheres in proximity, and then you watch how far it gets deflected gravitationally.
So what makes it deflect farther?
Well, right now they're so far away that there was effectively no gravitational. Well, right now it'd be evenly mixed between the two, right? But if I scoot them over like this, see now these are in close proximity, and so there's going to be some measurable gravitational force acting here and here, but they're both going to contribute.
So the lead ball's gravity attracts the small.
Yeah, exactly. Right. The gravitational force between these two is attracting them, and that's going to twist this torsional wire, which causes that mirror to get rotated, which deflects the beam, right? And because the light is being shown over a pretty large distance, a very small deflection makes that a measurable angle, right? So these are really small forces, and we'll do some calculations here in a second and see how small they are.
Wait, so if none of it was to move, would the light just come straight back?
Yeah, it would just come straight back, right? So if we run this backwards, see there it is in its rest position where the light's coming straight back on the laser. Okay, and then we run it forward. Okay, and now we can see what that deflection is. And we've got the instrument calibrated, so knowing what that deflection is tells us what the force was, right? Because we've already calibrated it. Here's one more little demonstration of that. I don't think this one really, that's more like what he did. He had that sodium vapor lamp, but you see what it's doing? Okay.
Would it return to its previous position like
Yeah, it would. And he demonstrated that there was.
So what was
Would
he?
it do that because the wire was getting twisted?
Yeah.
And it would just untwist?
Yeah, it's the same principle, when you hang your shoe by a shoelace and you spin it up, and then, yeah.
So what was he trying to prove?
Well, what he was proving was, what he did prove was, go away, cancel. Okay, there we go. What he did prove then, if we go back to this equation here, so he knew what the mass of each of those lead balls was, right? He measured what the force was with that real sensitive torsional wire, right, that measured the forces, the really tiny forces. He could very accurately measure the distances between the centers of mass, right? The whole instrument was calibrated. And so the only thing left in that whole equation was G. That was the unknown, and that's what he calculated. And he was pretty close. He was really pretty close.
Are we gonna be given that?
Oh, yeah. It's 6.67 times 10 to the negative 11. Really small.
yeah.
Okay, so that's the value.
G equals G.G7?
Okay. Yeah. 6 point, if you read my crap, you're right. Okay. So then, what can we do with this? So we can do some interesting things with this. Once we know that this is the universal gravitation law, then we can answer some interesting questions. We can say things like, we could talk about the amount of, well, it's a centripetal force, isn't it, right? So for example, if we have a satellite that's in orbit, this is the force that's responsible for keeping it in circular orbit. So it's providing the centripetal force, right? So for example, how fast, what if we were to do an experiment where we're going to go up to the top of a mountain and we're going to find like the mountain that's, if we study the geography of the Earth, we know that we can shoot this thing, we got to shoot this bullet at an elevation that's going to be just parallel to the surface, right, when it leaves the gun. And there's no other mountains that are going to get in the way, and it's going to go clear around the Earth and come back and we'll catch it, right? Okay, let's ignore some little things like air resistance and stuff, right? assume we had a really tall mountain, so it's high enough that we're above most of the atmosphere, right? We could determine how fast we'd have to shoot that bullet, right? Because we know, let's look at this. This is the force of gravity, right? So let's write this in terms of the mass of the Earth and, say, the mass of the bullet, okay? So the force acting on the bullet is equal to G times the mass of the bullet times the mass of the Earth divided by whatever the distance between the bullet and the center of the Earth is. Well, we're pretty close to the surface of the Earth, so we'll just call that the radius of the Earth, right? Let's assume we're doing this just right over the surface of the Earth.
Squared.
Okay, squared, yes. Okay, well then that's equal to, that's the centripetal force acting on the bullet, right? So by definition, that's got to equal the mass of the bullet times the centripetal acceleration, right? Centripetal acceleration, we could write in terms of v squared over r, right? Okay, so let's do that. Let's replace the centripetal acceleration with the expression v squared over r, and the r would be the radius of the Earth again, wouldn't it? Everybody agree? Well, notice what happens here. Here's my equation. Does anything cancel? Anything I could divide away from both sides? Yeah, mass of the bullet's irrelevant, isn't it?
Yeah.
Right?
Wait,
Doesn't make any difference.
but they're both on top.
Oh, it doesn't matter. Well, yeah, that's on top and that's on top, right? I could pull that out front if I want to, right? So then, if we want to, and that's supposed to be squared, isn't it? Where did I put the two? What's that supposed to be? I think that's supposed to be my squared, isn't it? I don't know what I was doing. So that's squared. So let's solve that for v, right? So all I'd have to do if I want to solve that for v is I got to get rid of the r on the bottom, so I could multiply each side of the equation by the radius of the Earth, right?
The radius of the Earth. Could you cancel that out?
This one's being squared, so I can't. But I could multiply each side by the radius of the Earth to cancel it from the right side, and then I'd have r over r squared, so now I could cancel one of those, right? Okay? So at that point, what have we got? Let's rewrite the equation then. So then we've got v squared on one side, and on the other side we've got this stuff. We've got g times the mass of the Earth divided by the radius of the Earth, and now all I have to do is square root both sides, right?
Yeah.
Okay, so then we come up with a pretty cool equation. We come up with the equation v equals the square root of g times the mass of the Earth divided by the radius of the Earth. So we can plug stuff in, right? We can figure out how fast that thing would have to go. So g is when I gave you this, when I gave you that number, I didn't include all the units, but it's just that's what it is in terms of standard units, right? So we'll just use standard units. So we end up with the square root of 6.67 times 10 to the negative 11th times the mass of the Earth is 5.98 times 10 to the 24th kilograms. So that's, and Cavendish helped us figure that out. And then the radius of the Earth is about, I think it's 6.6. No, I can't remember if it's 6 or maybe 6.2. I better look that one up. It's in our book. I think it's 6 times 10 to the 6 meters. I can't remember. It is avocado's number, huh?
Oh.
Earth radius. 6.38 times 10, so 6.38 times 10 to the 6 meters.
This is Listen.
Okay. So there's my saying. So what do we get? Somebody throw that. I'll throw it in my calculator. What's that give me? I don't trust you.
Oh, man, I was just about to. But if you got it.
All right. So we got the square root of the quantity. So I got to put all the top in parentheses. So you know how to do scientific notation numbers on here?
Yeah, second E.
There you go. Good.
What happens if you use the other E?
You mean which one? The lowercase e?
Yeah.
That won't work. That's the natural number. That's 2.7128.
Oh,
7128. Yeah. Yeah. Okay, so that times 5.98 to the 24. Pretty sure that's right. Almost positive. Divided by 6.38.
Mr. Oya.
Okay, there's only one number, so I don't have to.
What? It doesn't matter because it's just multiplying and dividing.
No, it would. Yeah, you're right. It wouldn't matter anyway. To the 6, and that gives us an answer of that.
I'm pretty sure that matters, Mr. Oya.
No, it doesn't.
Because it's like 4 times 5 divided by 6. Wouldn't that matter?
No.
Oh, no, because it's in the right order anyway. Okay.
Yeah, we'll make it difference. So then that gives us an answer of about 7,900 standard units of velocity would be what?
About 6 or 7.
What are standard units of
8.
velocity?
8.
Meters per second. So that's how fast the bullet would have to go to go around the Earth. It'd have to be going about 7,900 meters per second. So let's think about that in terms of feet per second, right? So that's going to be, a fast gun would be 35, what would it be? Fast muzzle velocity, 3,500 feet per second? That'd be pretty fast, right? Okay. So if we convert that to, let's just look for a conversion. I don't want to have to go through the whole thing. So convert meters.
Right, exactly. Feet in the yard.
Yeah, I was thinking yard.
Okay, so times
Do you not?
about 3.3 roughly.
Yeah.
So that'd be about 27 or about 26,000 feet per second.
Pretty solid gun.
So yeah, that'd be pretty fast, right? That's how fast it has to go for the bullet just to without.
Wait, would that be impossible to make a gun?
It wouldn't be impossible to make a gun that shoots something that fast, but the air would vaporize the bullet. Yeah. So
What if we shot a beam of light that fast?
you could never shoot a beam of light that
It'd be
fast
going up.
because it would always
That would
go.
be so slow.
The beam of light would go 186,000 miles every second. So
What
it's
about,
gonna go.
what about plasma? What if you shot plasma that fast?
You could.
Would you go all the way around?
What if you shot
Do
air that
physics
fast?
experiment.
Like, what are the physics
Bring a
behind
plasma
plasma?
rifle.
Well, we'll have to talk about that later.
Come on.
I say
enter
let's
the
go on
code
a
to listen
tangent.
to your voice on
What's that? Okay. All right, so then I got another question for you then. So we could do, and we could figure something out, like for example, we could take a different option. We could say, what if we wanted to put a satellite a certain distance up? Then what if I wanted to find the speed at which a satellite that's like 1,000 kilometers above the Earth's surface, how fast it would have to go? What's the only thing that would change here?
Radius.
The radius is the only thing that would change, and I'd have to just add that additional 1,000 meters, right? I said 1,000 kilometers, so what would that be? Million meters to this number, right? And that's just going to change the velocity a little bit.
7.3.
Okay, I got another important question for you though. How many of you have got? Raise your hand if you've got a satellite, like TV.
Like,
Yeah,
is that
dish
like
or
direct TV?
dish or direct TV.
So just normal TV.
Yeah, but not cable, but satellite. Satellite. Okay, so you have a satellite dish on your house, right? Okay, can you tell me what direction that
Towards the sun.
points? No. North, we say. Let's take a poll.
Angle.
No, it has to go south. It has to go south.
Okay, yours points south. Point south, okay.
Would it point?
East, you're saying?
No, it has to point south.
I'll throw a west in there.
We're trying to get DirecTV in my dad's house, and he lives on the South Hill. And the people at DirecTV were gonna, they were gonna put on, they said they could put it on because he lived on the South Hill, which made no sense because it's supposed to be.
Well, but the South Hill faces north, so.
But they still could have put it on. I mean, the people next to us.
Oh,
Really,
yeah.
the moral of the story is he's just bitter that direct.
Yeah, that's what I'm getting from this. Okay, but if you check, I guarantee what you're gonna see is that it points basically south, right? Okay, this is an important issue, so why? Why does it have to do that?
Because it's where we store all of our satellites.
No.
So.
No, satellites everywhere.
Exposed territory.
If we're in the northern hemisphere.
That's has something to do with it. Okay, hold it, listen, this isn't working, We gotta do this as a group, so.
Satellites like go around this way or something, we're in the northern hemisphere, so we have to point down or out?
Okay, you can see, but if you go out on a clear night and you just watch for a little bit, you can see satellites zipping all over the sky. I mean, they're going north, south, they're going in all kinds of weird directions. So why is it, you guys, you should get to be able to get to the bottom of this, you gotta be. It has to do with the pattern, it
Does it
does.
have to do with the equator?
It has to do sort of with the equator indirectly, yeah.
Because the magnetic field around the Earth.
No,
I don't get it.
now think about this, does your,
South is because cold, so there's more.
There's more Earth
You know
than
what I'm saying?
Yeah, I know.
It's a cold.
It just sounded funny.
no, somebody help me out.
Oh, we're
One at a time.
satellite being below us and above us.
No?
I don't know.
Can we
But
have
it's,
a hint?
but now, how does, think how this must work. You've got, those of you who have had satellite dishes, what happens if they get bumped a little bit?
Oh,
You
your
lose
TV's
signal.
trash.
TV's trashed. And then it's hard to fix yourself. You gotta go up there and twist it just the tiniest amount and have somebody yelling at you, okay, it's good. Now you screwed it up, right? Then you gotta move it, you gotta really carefully align that thing. How come?
Is that because of the angle?
It's really precise, right? Because the satellites, is it close? That's a long ways away probably, right? So you gotta get this thing pointed sort of right towards that satellite, which is a long ways away. But your dish doesn't move, it doesn't track some kind of satellite. The satellite's what's beaming the information to your dish. So you think there's always satellites, if there's always satellites moving through that area, that would be frustrating to watch then, because you'd always get, shows would fade in and fade out.
I mean, like.
So that can't be it. There must be something else going on.
Use the moves.
Okay, I tell you what, let's do, I'm gonna add one other equation here. I'm gonna add one other equation, so.
All of our
Some
TVs
things
running
are-
through the ISS.
Did they catch that goes around you from like
Tell you
a wide angle? And then just.
No, they're pretty precise. Okay, so let's calculate the period of a satellite also. We could do that, right? Because this is, we know that centripetal acceleration, that's really all this is if we divide the mass away, right? Centripetal acceleration, which is, we've got this guy right here, right? V equals 2 pi r over t. Let's just do it that way. So we have V, right? So we know that this must equal, yeah, this will be easier. So we know that this that's V, that must equal 2 pi r over t,
Yeah, exactly.
right?
Yeah.
So I want to solve for t. So all I've got to do then is I'm going to flip both sides. That's one way I could do this, right? So if I flip both sides of that equation, I'm going to get t on the top and 2 pi r on the bottom, and it flips this square root. So we've got the r sub e on the top and the g and the mass on the bottom.
What makes you able to do that?
Because I can flip both sides of an equation, right? If it's an equation, if it's an equation, then if I take the reciprocal of both sides are still equal, right?
It's just like
Okay,
one half
makes
equals
sense?
1/2 and 2 equals 2.
Right. Okay, so now if I want to solve for t, I got to multiply both sides through by 2 pi r, right? So I'm going to multiply by 2 pi r. So those cancel. And then I end up with this equation. I get t equals this stuff. 2 pi Okay, now let's look at this. If I multiply, okay, I'm not gonna do this anymore if you guys aren't gonna follow this. Otherwise, we'll just do other things, right? I thought this would be interesting. We wouldn't have to do a bunch of problems and things today. I thought we just kind of talk about satellite dish. Is that gonna work?
Yeah.
Okay, so R sub E, what happens if I multiply R times the square root of R? Think about your properties of exponents, because you guys told me yesterday that a square root's a 1/2 power, right? So that's like R to the 1 times R to the 1/2. That would be R to the 3/2, right?
Right.
Another way of thinking about that would be I could have an R cubed inside the radical, right? Because isn't R equal to the square root of R squared, right? You buy that? So if I put this into the radical, inside it would look like the square root of an R squared. So I'd end up inside the radical with an R cubed on the top and a GM on the bottom. So what I got there then is I've got some formula that gives me the period of the satellite's revolution around whatever it's orbiting as a function of its distance away from the center, right? The mass of the Earth, we're talking about Earth, I guess, and the universal gravitation constant. Well, those things aren't changing, right? But the radius is, meaning the height, the distance from the center of the Earth. Okay, now let's go back to our discussion. You don't have some kinds, it'd be a really expensive satellite dish if it could actively track satellites and stay pointed at them. But it doesn't do that. And as evidenced by the fact that if you bump it, right, or even if a really strong wind comes up and it shakes it, you have to have somebody come up and realign it, right? It's got to be very carefully aligned. So what does that tell you about the satellites then? It tells you something really important.
They stay in one spot.
They stay in one spot. How in the world can a satellite stay in one spot? Wouldn't it fall?
Is the satellite rotating around the Earth,
Aha.
orbiting at the
Aha.
Earth's same speed as the Earth?
The satellite is in what's called geosynchronous orbit, right? So it must be at just the right distance from the center of the Earth, so its period is equal to what?
The Earth.
24 hours, right. It must be exactly 24 hours, right? So think about that. The Earth is rotating, and then the satellite is revolving around the Earth, but it's revolving around at a pace that exactly matches the Earth, right? So it's always going to be aligned at the same spot over the Earth. Okay, now so we'll be able to calculate that easily, but why is it then? So that makes sense, right? So we're using geosynchronous satellites, but then why do you have to point it south?
The equator.
Our placement on Earth.
It's our placement on the Earth. Where's the only place that a geosynchronous satellite could ever stay motionless over the Earth?
South America.
It'd have to be over the equator, wouldn't it? Right? Because seen from the perspective of, I wish I had a ball in here.
Wait, so they only have one satellite?
So, yeah, like-
Well, there's a whole band of them, but Dish Network has a bunch, and the one for Oregon would be the one that would be kind of due south of Oregon. The one for New York would be the one that's kind of due south from New York, right?
So
See
are
what I'm
they
saying?
all located exactly at the equator?
Yeah, they're all exactly over the equator. Yeah, exactly. Okay, I need a prop here. Hang on.
I don't think TP would be.
It's
a-
like a
Been
little
that
yellow
time.
now.
No.
I fell asleep. Yeah, we know.
Just trying to go for a head.
We started talking about UK.
Every time. Were you waking me up?
When you fell asleep, we started talking about
Yeah.
it.
He tried to talk to me.
Okay, so here's my prop. So
Oh,
if-
bright light.
Right, like, so here's the Earth spinning, right?
Yeah.
Okay. So here's the equator, right? If a satellite is gonna spin with the Earth, it could only be right over the equator. What if what if we started it off over the North Pole?
Oh, that'd be fun.
Then it would have to, it's still gotta orbit the Earth, right? But then it's gonna be orbiting from the North Pole to the South Pole back to the North Pole. And what's gonna happen to the Earth as it moves down?
It's gonna pull it, so it's like,
Well, it's gonna be spinning relative to the Earth then, right? Because this thing's gonna be in the same circle all the time, but as you turn, if you're sitting right here, even though it might start off being in line with you, you're gonna turn away from it, right?
What about if it was like a little bit lower than the equator?
Wouldn't work. It's gotta be, even if it's a little bit lower, because if it's a little bit lower, then it would have to orbit the center, and it'd have to go from the southern hemisphere to the northern hemisphere and back, and so you'd see it wobble through the sky.
It
Right.
can't, okay, so it can't just go at a lower level.
Like at a lower level?
No, it's gotta be over the equator.
That makes sense.
So what do you
We're not
suppose is
seasons.
probably true? Do you think it's, that's coveted space then, around that band, right?
Oh, yeah.
Must be, right? It must be. Because everybody, if you want to have any kind of communication satellite, that'll always be at the same place relative to the surface of the Earth. It can only be in that band of space.
So is that where like
Are we ever
phone
gonna run
satellites
out?
are?
That's where all communication satellites
How
are.
full is that band?
Well, it's a pretty big band, as we'll see, but it's getting more full. And here's the dangerous thing. See, here's the thing that the more you know about this, the more
Oh God.
you kind of get scared, because it would be pretty easy for somebody to really cripple global communications, which would be a horrible. Can you imagine what that would do?
done that yet?
They don't
Right?
have to blow
That
up
is
one.
so-
Well, I mean, when I say easy, I mean not easy, but not as hard as you'd think. It's not like you'd have to have some kind of
Dude, that's
amazing
crazy.
spaceship. All you'd have to do is send a satellite in geosynchronous orbit in the opposite direction.
They're gonna take out
And have
every
it
single
take out
one.
one of them, right? And so it
Gravity
takes
up
out
here.
one of these satellites, and we're gonna see how fast they're going, and it's fast.
Some of the
Really
particles
fast.
keep going
So is
way.
that like where like the military, like their stuff too, like their communication?
Everybody's.
Everyone.
Everybody's. And so if you were to destroy one satellite with a collision, that's gonna be, blown into just millions of little pieces, some of which are gonna be traveling in the opposite direction around the Earth, and every time they hit a satellite and they destroy it, you get more debris, and it's a chain reaction. And pretty soon,
How is that not
Why
happening?
hasn't anyone done that?
well,
yet?
it's, okay,
Or like even just like
Dude,
little
that is when
comets or
Mercury is-
like little shards of rock.
Even try.
okay, there is a growing problem with that. There is and that's something that it's more dangerous now to be an astronaut in a space station than it was 25 years ago, because there's more debris from those kinds of things, from small collisions that's shooting around at many, many thousands of miles an hour, right, in the atmosphere, and stuff that's, we track it, but you can only track things that are bigger than a certain size, pretty small, but a lot of this stuff is really tiny, and so that would be I know for a fact that if you were gonna be an astronaut, you've gotta have all kinds of fail-safe maneuvers you can do. Like if you get into a place where they can see that there's a cloud of potential debris coming in, you got to get in the middle of the ship in this place. They're going to penetrate. I mean, it would be a bad deal, because it's gonna pierce the skin of the spaceship. It's the space station. It's really bad stuff. If you were outside, or if you were in a place that was unprotected, I mean, think about we'll talk about energy pretty soon. The bullet's pretty serious, but these would be traveling potentially, many hundreds of times faster than a bullet. And no matter how small it is, if you got that kind of velocity, tremendous energy. And so that is an issue. That's an issue that we're dealing with, and that's why it's so carefully regulated. Because there's all this debris that if it gets started, there could have to be a period of many hundreds of years before it'd be safe to put satellites back up again. That's one.
That ISIS doesn't know about this.
That's right.
I'm pretty sure they do. I just don't think they
I hope they don't see my YouTube video. That could be bad.
You're the links that Trump's been talking about, right?
Yeah.
Yeah.
Okay, so what I want to do, last thing I want to do today then, is let's figure out this whole deal with the geosynchronous satellites. Let's figure out how high they have to be. That'd be kind of interesting.
So, would you say that your knowledge of this is enough?
Is threatening to national security?
Yeah,
I need to be-
you could.
Not
you
all
could-
of our knowledge is of it.
Yeah, now you all know. I put you all in jeopardy. You're all.
We're all
it's-
terrorists now.
That's right. You're
We're
all.
obviously
You're all
making
going to be on a
money
list
to
somewhere.
build this
Yeah.
satellite and launch it into space.
We can't go on it.
Okay, so this is pretty easy to solve, right? What the period
Or buy
is.
fertilizer.
All we'd have to do to find R here, right, would just be to plug in the period that we want, which is 24 hours, right? So that's, what is that going to be? In terms of standard units, that's going to be 24 times 3,600 seconds per hour, right? So, and we're going to solve for R. So let's go ahead and square both sides of this thing, right? Does that make sense? We square both sides, and we're going to get t squared equals 4 pi squared times, not square root, we got rid of the square root, times r cubed over gm, right? We want to get that by itself. So let's divide both sides by 4 pi squared and multiply by gm. Everybody agree?
Yeah.
So that's going to give us radius cubed equals, let's see, T squared G M, because those go to the top, right? Divided by 4 pi squared. Then all I have to do is cube root both sides, right? To get rid of the cube. And we got ourselves an equation. Now we can just plug and chug. Okay, so let's plug stuff in. So what's that going to give us then? I'm kind of curious to know. So we've got the quantity. We've got the quantity T, and we said that was going to be
20, oh, like
Bing
24
bong.
times like 37.
Oh. Okay. I'll put the other assignment up. You guys can get going on it. We'll finish this up tomorrow. I got to know. I got to know how high these satellites are.
Thank you all very much.